Welcome to the eigenvalue eigenvector class. So as we have already seen in the lecture, now we are going to elaborate more examples and some more properties of eigenvalues eigenvector in this lecture. So eigenvalues eigenvector, any system of equation ax equal to lambda x and x is non-zero vector. If such non-zero vector satisfy this condition, we call it as a lambda is an eigenvalue corresponding to eigenvector x, right? And assume that you are working in R2 and you have some vector, right? So what had happened, I'm going to this, let's say this is your x vector, right? So if I'm going to multiply x and if I get lambda times of x, what does it mean? You see, lambda is a scalar. What does it mean? Scalar means if you see, if I'm going to increase, if I'm going to multiply, what had happened? This vector becomes twice of its length. Twice of its length means lambda become 2, right? And if I'm going to multiply, if I'm going to get, let's say, opposite direction, it means lambda equal to -1 because same vector with negative direction, minus x, opposite direction. You got it? So it means we are we are searching this oscillatory behavior of those vectors after multiplying this matrix. So we are searching how many such vectors are there which will oscillates with the given matrix, right? In the same direction. Oscillation will be in the same direction or opposite direction. So those special vectors we are going to search, right? And corresponding to those vectors, corresponding to those lambdas, we are going to get such non-zero vector, which is very, very important here. Okay. So if I see the properties of the eigenvalues and eigenvector, so a good remark here is eigenvalues of a matrix, of course, this is a square matrix, can be real or complex, right? Eigenvector corresponding to distinct eigenvalues, right? If I'm having distinct eigenvalues, so eigenvector corresponding to distinct eigenvalues are linearly independent, right? And symmetric matrices. So in symmetric matrices, we have real eigenvalues and orthogonal eigenvectors. These are the properties, right? Similarly, if we have skew symmetric matrices, so in skew symmetric matrices have purely imaginary or zero eigenvalues, right? We have another formula. If I want to know what is the determinant of a matrix, and if I have been given all the eigenvalues, then I'm going to get multiply all the eigenvalues to receive the determinant of the matrix. So this result says determinant of a matrix A, square matrix A, is nothing but the product of the determinant. So for example, if you have been given a matrix A, right, of size 5 cross 5, and you have been told that the one of the eigenvalue is 0, lambda 1 is 0, right? One of the eigenvalue 0. What can you tell about this matrix A? So this matrix A means determinant will get, let's say, lambda 1, lambda 2, and so on, lambda 5, which means lambda 1 is 0 into all of them non-zero, lambda 1, lambda 2 to lambda 5, so which will give you 0. Determinant of A is 0. What does it mean? This matrix is singular, or in other word, this matrix has no inverse or non-invertible. You got my point or not? So many information you can infer with the help of eigenvalue for the given matrix, because of the fact that determinant is going to be the product of the eigenvalues. Another property, another property is trace of A. Trace is nothing but the sum of the Trace, what is a trace? Trace means sum of the diagonal element. So if you have a matrix, sum of all the diagonal element becomes a trace. So if you have lambda 1, lambda 2, lambda 3 and so on, then trace of the matrix will be the sum of the eigenvalue, right? You got my point or not? So suppose if you have some matrix, then 1, 2, 0, 2, then 1 plus 2 is equal to trace here. 1 diagonal entries 2, and then if you get the eigenvalue of this matrix, you will also get 1 and 2 eigenvalues, lambda 1, lambda 2. Simple case I'm taking here. So which is the sum of these two. Okay. So trace of A is nothing but the sum of the diagonal elements, right? And which is equal to the sum of the all eigenvalues. Okay. Another case, diagonal matrices have all eigenvalues as the diagonal entries. If you have been given a diagonal matrix, right, then you are going to get just eigenvalues as the diagonal entries. If you solve Ax equal to lambda x, you will get the same procedure, but directly if you can read out the diagonal entries is going to become your eigenvalue. Directly you can read without solving this characteristics polynomial and all. Okay. But if it is asked in exam, then you have to follow the complete procedure. But for objective question papers and all, you can very much easily see the diagonal and read them and what are their eigenvalues. Okay. Similarly, upper triangular and lower triangular. Upper triangular means the matrix diagonal form here non-zero and here zero entries, right? Zero. Okay. Diagonal upper triangular. This is upper triangular. And similarly, lower triangular means below the diagonal, all entries are there. Above the diagonal, entries are zero. So upper triangular and lower triangular matrices have all eigenvalues as the diagonal entries, similar to the diagonal matrix. Now another important remark here is uh, block diagonal matrix, all eigenvalues as the union of the eigenvalues of the diagonal blocks. Okay, so let us see one example. So eigenvalues and eigenvector example. So let us say A is a matrix 4, 2, 1, 3. Find eigenvalue lambda by solving A minus lambda equal to 0 determinant, and then this extend to determinant you are going to solve A minus 4 minus lambda 3 minus lambda, it is being subtracted from the diagonal, and then you find the characteristics equation. Once you find that characteristics equation, then you can say what I can say, this equation can be easily written if you see lambda square plus you know trace of A into lambda, right? Lambda square minus trace of A minus trace of A plus product of product of you know product of your or you can say determinant determinant of A. So you can find the characteristics polynomial easily. You see A is given. What is trace of A? Trace of A is the sum of the diagonal entries 4 plus 3, which is 7. What is determinant of A? Determinant of A is this into this minus this into this. So 12 minus 2, which is 10. So if you see the equation, lambda square minus trace of A. Trace means minus, trace is 7. 7 into lambda, and then determinant of A plus determinant of A is 10 is equal to 0. Directly you can write characteristic equation, right? So using the trace and determinant property. Okay, so now solving the characteristics equation, we got lambda equal to 5, lambda equal to 2. So lambda 1 I declare 5, lambda 2 I declare 2. So now solve for lambda equal to 5. You have to plug in place of lambda 5, a minus 5v equal to 0. And then when you solve this system, you need to reduce into R, R, E, F. So you can say swap the rows. So what you will get 1 minus 2 minus 1, 2, right? And then you just make this is a pivots, add it to this. So what you will get 1 minus 2, and then you will get 0, and then you will get 0. So you are having only one pivot entry and another variable, no pivot entries. It means that x2 is free variable. Okay. So now you can write the solution. X1 is equal to 2x2, and then when you take x1 as 1, you will get non-zero vector, right? So free variable, and then you can say that x non-zero, any value you can take. So for one value I have received one eigenvector. Similarly for minus 2, you will get the another eigenvalue vector 1 minus 1. Okay. So now verification result, whether you have obtained the correct result or not, you have an equation. So verify a into v1, right, equal to lambda, you will receive ax equal to lambda x. Verification I am doing. So a is already there, x you have obtained, so ax. Then check whether you have done correct uh, calculation or not. Then you should receive the same lambda into x. So this is correct. This is for this second, lambda equal to 2. So both are correct. So this is the verification for your point of view. Suppose if you are doing any problem in exam, then how do you verify? This is the verification point purpose. Now, example of symmetry matrices. We know the symmetry matrices has real eigenvalues. So you can take this is a symmetry matrix, right? Symmetry matrix means A equal to A transpose, right? So row change by column, you will get the same matrix. Okay, characteristics polynomial you can write. Eigenvalues eigenvalues are 3 and 1. So corresponding to 3, corresponding to 1, you are going to get. So this eigenvalues are real, as we have already stated in the property. Skew symmetric matrices. If you see skew symmetric matrices, so skew symmetric matrices has eigenvalues uh, 0 are complex. Since order 2 cross 2, so 0 will never occur. 2 cross 2 means root occurs in pair, right? Suppose if it is a 3, A is 3 cross 3 and is a symmetric matrix, right? Suppose the question is being asked, A is a 3 cross 3 matrix, skew symmetric matrix having one root 2i. What are the other possible root? So 2i, so complex root exists in pair, right? So minus 2i will be another possible eigenvalue, right? And since root occurs in pair, so one root is left over, so we can write 0. So this is the possible roots for the given matrix. Okay. So similarly, you will get the eigenvector corresponding to it. Now the diagonal matrix. Block diagonal means if you see this is a one block and this is another block. Means A can be written as C big 0, D big 0, D, where C and D are submatrix, right? So submatrix, a smaller matrix. Okay. Then if you see it here, the block element. So this is purely a diagonal matrix. So roots are 2 and 3. And this is upper triangular matrix, right? So roots are this. So directly you can find out the eigenvalues while looking the matrix without solving Ax equal to lambda x if it has some special type like block matrix or diagonal matrix, upper triangular, lower triangular, and so on. And there are several applications. It will be used in principle of component analysis to reduce dimensionality of the data, solving differential equations, especially linear differential equation and mechanical system, analyzing vibrations and stability, writing, uh, right, quantum mechanics, representing physical observables, right, and Google page ranking, ranking web pages based on the eigenvector centrality, right. There are few more important properties which I am going to list here. If A is n cross n, right, matrix, A is n cross n matrix, and if I'm going to say that like lambda is an eigenvalue of A, then then first eigenvalue of A inverse. I want to know what is the eigenvalue of A inverse, right? Is lambda inverse. That means 1 by lambda. That means lambda should not be 0, right? Which means A inverse exist means what? A must be what? A must be singular, non-singular. A is non-singular. Because if A is non-singular, then you are able to talk about the inverse of the matrix, right? And suppose alpha is any scalar, right? And eigenvalue of then eigenvalue of alpha A. You are going to multiply by alpha. Since I know eigenvalue of A is lambda, so eigenvalue of alpha A is alpha lambda. Simply multiply by lambda, right? Alpha lambda, where lambda alpha is a scalar. Okay. Third property, for all n belongs to n natural number, an eigenvalue of a to the power n is lambda to the power n, right? Which means a square eigenvalue has lambda square, a cube eigenvalue has lambda cube, a to the power 2025. What is an eigenvalue? Lambda to the power 2025. Simple cases. Okay. And one more, eigenvalue of adjoint of A, okay, is determinant of A divided by lambda, provided lambda is non-zero, right? So these all are some listed properties. I hope you have understood. So thank you very much. Thanks a lot.